So we're in Chapter 7 now, Analytic Geometry, and the first section is just called Conics, and the objective is to know the names of the conics. So the three types of conics that we'll be studying are parabolas, ellipses, and hyperbolas. So hyperbolas. So I'll be bringing a cone into class, and I have this little interactive figure that I'll show you so we can see why these shapes are called conic sections. So people say conics for short, but they're actually conic sections. Okay, so the first type we're going to talk about is parabolas. And the big thing you need to keep in your mind is that these parabolas aren't necessarily functions. They might be, because the parabola could open upward or downward like the functions we've been talking about. But we can also now have parabolas that open to the right or to the left, and those clearly are not functions. So conic sections in general aren't functions. There's a few that are, the parabolas that open up and down. But in general, they're not functions. So we've left the world of functions and entered the world of geometry. So the first thing we're going to do is analyze parabolas. And to keep things simple at first, we're going to have the vertex at the origin. So we're just going to look at parabolas that have the vertex at the origin at first. And then we're going to analyze parabolas that have been shifted until the vertex is HK. So fortunately, that's the same lettering system that we used when we talked about parabolas that were functions, where the H and K are the coordinates of the vertex. And then the last thing that we're going to look at is solving applied problems. There's lots of really interesting applied problems that involve conic sections. So we're going to look in this section at those that involve parabolas. Okay, so we're going to start with the vertex at the origin. And we're going to have a new definition for a parabola. Okay, so a parabola is a collection of points in a plane that are the same distance from some fixed point, capital F, as they are from a fixed line that we call D. So this line D, well, let's start with the point F is called the focus, so F for focus. And the line D is called its directrix. So that's from Latin. And as a result, a parabola is a set of points for which the distance from the focus to a point on the parabola, P, is the same as the distance from the point to the directrix. So you can see that the vertex is always going to be right in between the focus and the directrix. And then you just draw lots of other points that are equal distance from the focus and the directrix. And each of those points P, when we get so many of them that they get so close together we can't see the space in between, we indicate that by drawing it with a solid line. But keep remembering that yes, it is a shape and we draw it as a line, but it is a collection of points. These are individual points. Okay, so then I have another interactive figure to show you in class that demonstrates this really well. So we're going to look at a theorem that says if I have a parabola with the vertex at 0, 0, and the focus is at A, comma 0. So now the focus is to the right or left instead of up or down. So this is the kind that are definitely not functions. So if I have A is greater than 0, the focus is always inside the parabola, and the directrix will always be an equal distance from the vertex. So this line is the directrix x equals negative a, because this point would be a distance a to the left of the vertex, which is at the origin. So then the equation for all of the points that are on this parabola is y squared equals 4ax. So the important things here to notice are the squared term is isolated all by itself on one side, and that this quantity 4a is important quantity. We're going to talk about it later, but I'll tell you now its name is the focal diameter. So 4a is called the focal diameter. A is the distance from vertex to focus and vertex to directrix in opposite directions. So see how the line segment that joins the 2 points a, comma 2a and a, comma negative 2a, this line segment here has a special name. It's called the latus rectum. So this is the latus rectum. Its length, oh my gosh, is 4a, which is the focal diameter. So this says at the focus, the width of the parabola is 4a, so it makes it really easy to draw the parabola. So here's some little tables out of your book if you like tables. So its length is called the focal diameter. Let me fill that in there. I'm not a big fan of tables. I'm a way bigger fan of holistically learning about these and drawing pictures and understanding how the parabola is put together. Okay, so let's look at some examples. This says find the equation of the parabola that's described and find the 2 points that define the latus rectum and then graph the equation. So I'm going to encourage you to always draw pictures for these. So here I have the vertex at 0, 0. And the focus is at 0, 2. So we know the parabola has to open upward because the focus always has to be inside the parabola. So it can't open right, left, or down. That's our only choices here. Well, where I start is the parent graph y equals x squared. I know that's the upward opening parabola. So I know what I'm going to write looks something like y equals x squared. But in this case, the x squared is going to be by itself, and I'm going to have x squared equals 4ay. The focus is not a point on the graph, so this equation is not going to be true for the point that is the focus. But what we do know is this distance from focus to vertex is 2, and this is what a is. So I have x squared equals 4 times 2 times y, or x squared equals 8y. So this is the equation of the parabola, this part here. Okay, now let's find the 2 points that define the latus rectum. So at the focus, 4a equals 8. So at the focus, the parabola is 8 wide. Well, we start at the focus, that means we go 4 one direction and 4 the other direction, so that it's a total of 8 wide. And then it's so easy to draw the graph. And don't forget to label your axes. So the 2 points, see, I can read them off my graph now. 1, 2, 3, 4, comma 2. And negative 1, 2, 3, 4, comma 2. And then just as a double check, notice that the distance between negative 4 and 4 is indeed 8. So I feel really good about that. And I've also graphed the equation. So we'll look at 26 together in class. It's a little bit trickier. So now we're going to let the vertex move to HK. So when you think about it, the whole parabola goes with the vertex. So H is going to be some kind of a horizontal shift, and K is going to be some kind of a vertical shift. So the thing that's different now, though, is that we're not just looking at functions. So the horizontal shifts work a little bit differently. So let's look at some examples. Here's the tables from your book if you want to do this by tables, but I'm going to really encourage you to do it by thinking and drawing pictures. So the first example says, find the equation of the parabola described. So I'm going to draw a picture and I'm going to say the vertex is at 1, 2, 3, 4, -2. So here's my vertex. The focus is at 6, -2. So see, by drawing a picture, I can see that it needs to open to the right because the focus has to be inside the parabola. So that's the only way it can open. And then I see that the distance from the vertex to the focus is 2. So that's going to be my A. So then 4A must be 8. Well, if y equals x squared is the parent graph for this guy, then it must be x equals y squared is the parent graph for this guy. So that's how I remember. I remember y equals x squared, and then I know if it opens sideways, it has to be the other way around. So the y squared is going to be by itself on one side. The 4a is going to be on the side where I don't have a squared. And then the coordinates of the vertex go here, y minus the x coordinate of the vertex, and x minus -2, which comes out to be x plus 2. So this is the equation of the parabola that has a vertex at 4, -2, and a focus at 6, -2. Okay, so now I know that 8 is the focal diameter. So I start at the focus and I go 1, 2, 3, 4 up, 1, 2, 3, 4 down, and I can draw the parabola. Make sure you label your axes. And then I can look at my graph and say 1, 2, 3, 4, 5, 6, 2 is one of the points on the lattice rectum, and 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 6, -6 is the other point on the lattice rectum. Notice they're lined up in the x direction, so they have the same x coordinates, but their y coordinates are 8 apart, so I feel sure that's correct. Okay, so we'll look at number 32 together. And to make it open to the left, you would have a minus in front of the not squared side, right? Okay, so for the remainder of the section, the directions are just going to say analyze the equation. And you have to know that that means to find the vertex, focus, directrix, and graph. Okay, so the thing that we're going to need to be able to do is remember how to complete the square. So let's do one of these together, but I'm going to make another movie so that this doesn't get too long.